All right, let's talk about an algorithm that actually loves chaos. It's a way to track things that don't follow a neat straight line. Like a self-driving car in messy traffic, or even the unpredictable path of a hurricane. It's called the particle filter, and its whole philosophy is about embracing uncertainty instead of trying to fight it.
Here's the fundamental problem we always run into. Our models, our equations, they're often designed for this perfect, ideal world where everything is clean and predictable. But we live in the real one, which is full of twists, turns, and total surprises. So, the big question is, how do you build a system that can accurately track something when reality itself just refuses to play by the rules?
To really get why the particle filter is so cool, we first have to look at one of the all-stars of estimation theory, the Kalman filter. It is a brilliant, brilliant tool, but it has this one critical weakness when things start to get, well, messy.
See, the Kalman filter works like an absolute charm, but only if you follow its very strict set of rules. It assumes the system you're tracking moves in a linear way, basically no sudden swerves or weird changes in speed. It assumes any randomness or a noise fits a perfect bell curve, and, maybe most importantly, it puts all its energy into tracking just a single, best guess of where something is. When all those things are true, it's unbelievably accurate.
But just think about something as everyday as city traffic. When is that ever neat and predictable, right? Almost never. And this is exactly where those elegant, perfect world assumptions start to completely fall apart.
In reality, traffic jams just appear out of thin air. The way cars bunch up at a red light is this super complex, non-linear dance. And sometimes, let's be honest, our sensors just fail and give us total garbage data for a second. Every single one of these things breaks the Kalman filter's rules, and that causes its one best guess to drift farther and farther away from what's actually happening.
So, if the real world is just too messy for one neat, tidy estimate, what's the alternative? Well, this brings us to the wonderfully elegant idea behind the particle filter. The basic building block here is something called a particle. And a particle is just about the simplest thing you can imagine. It's just one hypothesis. Think of it as one possible guess. So going back to our traffic example, one particle might guess, I think there are 21 cars. Another one might guess, nope, I think there are 35. It's just a single possibility.
And here is the giant conceptual leap. Instead of putting all our faith in one single best guess, the particle filter says, let's use thousands of them. This is way more than just a technical detail. It's a totally different way of thinking. We're not tracking one single point of truth anymore. We're now tracking a whole cloud of possibilities, where every single particle in that cloud is a different guess about the state of the world.
Now this cloud isn't just a static bunch of random guesses. Oh no, it's intelligent. It evolves, it adapts to reality through a really simple but incredibly powerful repeating cycle.
It all boils down to this four-step loop that just runs over and over again. First, you predict. Every particle makes its own guess about what's going to happen next. Second, you weigh. A real-world measurement comes in and we check how well each particle's guess lines up. Third, you resample. This is kind of like survival of the fittest for our guesses. And finally, you estimate. We calculate the new best guess from this smarter, more focused cloud. And then the whole thing starts right over.
That weighing step is really where the magic happens, where the algorithm touches reality. For every single particle, it just asks us one simple question. How well does your guess match what our sensor just told us? Guesses that are close to reality get a high weight. Guesses that are way off in left field, they get a really low one.
And this slide shows that process perfectly. So imagine our sensor took a measurement, and it was closest to the guess made by particle B. Well, as you can see, its bar is way, way taller. It gets a much higher weight. The other particles, whose guesses were further off, they get these tiny little weights. The algorithm is basically saying, okay, let's pay a lot more attention to the guesses that actually seem to be right.
And that leads to the next brilliant step, resampling. To create the next generation of particles, we actually draw from our current set based on those weights. This means a particle with a high weight is probably going to be copied multiple times into the new cloud. And those low-weight particles, they'll most likely just disappear. We are actively getting rid of bad hypotheses and multiplying the good ones.
Okay, so that's all the theory. Let's make this way more concrete. We'll run through a quick and simple numerical example using our traffic jam scenario.
All right, so the algorithm has made its predictions. Now, a new piece of real-world data comes in from our road sensor. It measures a queue of 26 cars. This one number is the piece of reality we're going to use to update our entire cloud of possibilities.
And here it is, the aha moment. Take a look at this table. Particle 2, which guessed 25 cars, and Particle 3, which guessed 28, were the closest predictions to our actual measurement of 26. Now look at their normalized weights, 0.37 each. They're huge. Now compare that to Particle 5, whose guess was way off. Its weight is a tiny 0.20. The algorithm has instantly figured out which hypotheses are plausible and given them a massive boost.
And so when we calculate the final estimate by taking the weighted average of all the particles, we get 26.5 cars, and that is a fantastic result. It's obviously influenced heavily by that real-world measurement of 26, but it didn't just blindly accept it. It used the entire distribution of possibilities to land on a really robust, stable estimate.
So let's bring this all the way back around and put the two methods we've talked about in a direct, head-to-head comparison.
This table really just lays it all out. Where the Kalman filter demands those clean linear models, the particle filter says, bring on the non-linear chaos. Where Kalman needs that perfect Gaussian noise, the particle filter can handle noise of pretty much any shape. And maybe the biggest difference of all, while the Kalman filter gives you just one answer, the particle filter gives you the full distribution, a much, much richer picture of what could actually be happening.
So, what does this all really mean? It means the particle filter is basically built for the messy reality we all live in. It's great at handling abrupt changes, like that sudden traffic jam. It can track multiple possibilities at the same time. And it's incredibly resilient to bad sensor data, because a few weird measurements aren't going to completely derail the entire estimate.
This leaves us with a really fascinating thought to end on. This technique, this idea of using a cloud of hypotheses, it's not just for traffic. It's used in robotics, in economics, in weather forecasting. It's a whole new way of thinking about uncertainty. So the real question is, if we can now track chaos by embracing possibilities instead of demanding certainty, what else could we finally begin to understand?